Good morning, good afternoon, good evening, wherever you are. Welcome to this 12th webinar organized by Eijkelkamp North America on CPT. And what we're going to talk about today is performing CPT in accordance with the standards. What we're going to talk about today is probably one of the more, to some at least, boring parts of CPT, and that is performing CPT in accordance with the standards. I used to teach a course at the University of Texas for a number of years called Codes and Standards. And a lot of people have this aversion against standards. It's boring reading, but at the same time, it's important. And over the last year, we've covered all kinds of aspects of CPT. So it's about time now that we start looking at what does the standard really say, and then how can you make sure that you do perform CPT in accordance with the standard. When you look at CPT around the world, whether it is here in the United States or in Europe or in other parts of the world, there are basically very little differences between the equipment that is used for CPT, whether it's from one manufacturer or the other. As I mentioned many times before in this series, it is highly standardized. And the procedure that is used around the world is all, again, almost the same. And the reason for that is that you see the two standards here for electrical CPT, the ASTM D5778, the ISO 22476-1. Those two standards obviously are utilized in different parts of the world. You may perform it according to ISO, you may perform it according to ASTM, but the content, the procedures are almost the same. There are some minor differences that I won't go into today. But by and large, it's the same type of procedure, and it does not just apply for electrical CPT. Same thing applies to mechanical CPT. You see the ASTM and the ISO standards there. Also, before I forget it, just a quick reminder: what you see with the ISO standard is 22476-12. Quite often, people then think that when it comes to the ASTM standard, they also need to put in the dash, because as you see on the picture on the left-hand side, the top you see there, that the designation for the mechanical CPT standard is D3441-16. The dash part for ASTM and ISO are completely different though. In ASTM case, just the year that the standard was published, and in the ISO case, it's actually part of the number. Because if you go back to what we said for electrical CPT, there you see it's 22476-1. The electrical CPT is the first testing method that is being described, and then when it comes to mechanical CPT, it is -12. In case of ISO, you need to include the dash part. In case of ASTM, it's really not necessary. Now, the only way that you make sure that the test is performed in accordance with the standard is please read the standard. Get a copy of the standard. If you are involved in doing CPT on a daily basis, make sure that you have a copy of the standard, whether it's the ISO code or the ASTM code, in your rig, on your truck, because you never know if somebody comes there and starts asking you a question. Don't rely on this presentation. And it may sound weird, because normally when people give webinars like this, they say, well, we're telling you everything there is to know. I will just touch some major points in here. There are plenty of other things that I will illustrate it a little bit later. There are plenty of other points that I don't have time to cover in this half hour. So don't rely on this presentation. It will give you a flavor of what you need to do to perform CPT in accordance with the standards, but there is more than this presentation will contain. Also, for the benefits of this presentation, I will just focus mainly on the layout of the ASTM standard 5778, and go through some of the chapters that are there. The ISO standard is organized slightly different, but most of the same content is there one way or another. And what you see here on the screen are the 14 chapters or the 14 sections of the standard. It goes with the scope, what does this standard cover, some reference documents, a terminology, so to all use the same terminology as we talk about CPT. And again, for those of you for whom English is not the first language, may be useful that you look at it to see what, at least in English, the standard terminology is. And that's a terminology that I've been using in these webinars throughout. Then we have a summary of the test method. Now, why do we use CPT? Talk about interferences, the apparatus, and then you see on the right-hand side some more information, the hazards. How do you calibrate your system? How do you prepare or condition your system? And then finally, how do you actually perform the procedure, do your calculations and the reporting? Now, to illustrate the point that I made earlier, that why it's important that you read the standard is that in the standard, we talk about hazards and interferences. Nothing to do with that you perform CPT in accordance with the standards, but the standards give you very good clues about what may go wrong, what may interfere with your CPT. So those chapters alone make it worthwhile to read the standard and to go through this whole thing. That is introduction. Let's go back to what is CPT. Those of you that have been part of this webinar series before, you've seen this picture, you've seen this text, but let's just go through it quickly one more time. You see on the right-hand side a CPT truck, and it can be any type of carrier that brings the pusher to the job site, a crawler, a truck, whatever, and that pushes CPT rods into the ground at a speed of 0.8 inches per second or 20 millimeters per second. And at the end of those rods is a cone, and you see that enlarged because that cone then measures the tip resistance, the pore pressure, and the sleeve friction. And also it has the inclination in there, but most of the time the real measurements that you need for geotechnical purposes are the tip resistance, the sleeve friction, and the pore pressure. And we record that in case of Eijkelkamp and most other manufacturers every 10 millimeters or every 0.4 of an inch until the cone reaches the target depth or refusal. Now, if you need to do an investigation down to 20 meters, fine, and you stop there. If you cannot go any deeper because you don't have enough pushing force, which is refusal, then obviously you have to stop there. That is what we've talked about at several instances, what CPT is all about. Now, let's go look at the standard. Let's look what the standard says about the summary of the test method, which is chapter 4. Starts out, it says that a cone is advanced through the soil at a constant rate of 20 millimeters per second. Well, that is exactly what we were talking about earlier. So it makes what we've been saying all along is still there. It also talks that the cone tip, the force that is on the cone tip is measured with an electric transducer, and that we then come up with this tip resistance as the force divided by the cone base area. The cone base area, you know, that's the name of the cone. If you have a 10 centimeter square cone, that is then your cone base area. So nothing there, that's what we're doing. Well, the next part in 4.2 is the friction cone. And the friction sleeve is behind the cone. There we measure the sleeve friction, and again the resistance is then that force on the friction sleeve divided by the surface area. Nothing new, nothing surprising. Most modern cones are capable of registering pore water pressure. You hear me always when we talk about cones that do measure pore water pressure. It used to be many years ago that not all cones did that. That's why we then had the designation CPT versus CPTU, where CPTU indicated that you measure the pore water pressure as well. These days, most cones register pore water pressure, and that's why when I talk about CPT, I automatically assume that we're using a piezo cone, that is a cone that can measure that pore water pressure. And finally, it says that those measurements, the readings are taken at intervals of no more than every 50 millimeters, and improved resolution may be obtained at 20 or 10 millimeter interval readings. And as I told you before, the Eijkelkamp system and most other systems do it every 10 millimeters. So we're actually getting this improved resolution. If you are pushing a cone, you might as well just record all that data. Why would you not? You can always filter it out later on, but if you don't record it, you don't have it. So chapter 4 is very simple. We know that, we have been doing that, no problems there. Let's then look at the apparatus. That is where I want to start beginning to show you that some of the responsibility to perform the CPT in accordance with the specifications is the responsibility of the equipment manufacturer. Obviously, when you buy equipment, you can assume that the equipment is in accordance with the specifications. That is what the manufacturer promises you. But as you start using that equipment, it becomes your responsibility to make sure that it remains in accordance with the specification. And I will give you two examples of that. First has to do with dimensions. I don't want to go through all the dimensions, but we've talked about in the past that the cone is highly standardized, that all the dimensions are very well defined. And what you see here are the dimensions from both ASTM and ISO for the cone tip on a 10 centimeter square cone. And you see that the shoulder, at the base, the diameter has to be between 35.3 and 36 millimeters. Very small tolerance, not much leeway there. You also see that the height HC, the tapered part of the cone, has to be between 24 and 31.2 millimeters. There you have a little bit more of a range, but it basically means that as you're pushing your cone in the ground time and time again, the tip starts to wear, and you need to make sure that those dimensions are still being maintained. That's your responsibility, not the equipment manufacturer. You need to make sure that you keep doing it, because you don't want to do a CPT sounding only to find out when the inspector comes to the site, says, well, your cone tip is not in accordance with your specification, and therefore this won't count, you have to redo it. So just make sure that you keep that in mind. Another example is the filter elements. We said before, when you measure the pore pressure, the dynamic pore pressure, you need to make sure that your system is completely saturated, because the presence of air in the system would affect those dynamic readings. And the code also says that you should use pure glycerin or silicone oil. And if you use water mixtures, and quite often people are using a mixture of glycerin and water, you can only do that if the entire sounding is submerged, i.e. underwater, or if the dynamic response is not important. And I want to focus on that last part. If the dynamic response is not important, let's go back and say, what are we measuring with these pore pressure readings? We're measuring the dynamic pore water pressure, because as we're pushing the cone in the ground, you have a dynamic effect, and therefore you get that black line on the screen. That is what we are really measuring. That's not necessarily the equilibrium pore water pressure, or the pressure due to the water table, the hydrostatic pressure, because the dynamic effect of the cone, that is what you measure. Now, what are we doing with the dynamic water pressure? You see here the standard soil behavior types, and on the right hand side you see the correlation between the cone resistance, and on the horizontal axis the pore water factor, and that is a function of including the U2, and that's the dynamic pore water pressure. So if you want to use this soil classification chart, you need to have accurate readings of U2, which means you have to have accurate readings of the dynamic pore water pressure, which means that you need to have a saturated system. So I really don't know how people can say in the code, if you go back, what the code says, that the dynamic response is not important. That's number one. Number two, CPT results may be laying in a drawer and not be used or reused again after 5, 6, 7 years. How do you know whether the pore water pressures were taken correctly or not? There are no notes there, so you have to account or assume that the dynamic responses were properly accounted for. Therefore, the system was prepared properly. Therefore, you have used the right fluid to saturate your system. That's something that you need to keep in mind. Okay, that's about the apparatus. Partially your responsibility, partially the manufacturer's responsibility. Same thing applies to calibration. Obviously, you should assume that when you get new equipment in, that the equipment has been calibrated by the equipment manufacturer. Makes perfect sense. Then the code starts saying that the equipment should be calibrated after every repair. Well, some of the repairs may be done by you in the field. You may replace a tip, you may replace a sleeve, you may do something with that. You may not necessarily send it back to the manufacturer or to a service station of that manufacturer, which means that you have the responsibility to make sure that it stays calibrated after every repair. Then there's another part when it comes to calibration, and it is, in a way, the beauty of CPT. The code says that the equipment calibration should be checked before and after every sounding. So every time you perform a CPT sounding, you push that cone in the ground, you need to check the calibration. Obviously, your responsibility. Most of the programs that you use, the data acquisition programs, will tell you that you have to do this check. We'll tell you in a second what it is. And when you come back out of the ground, you have to also do that check. If the check doesn't pass, if the results are not acceptable, the program will warn you. You can override it. Nobody will find in your report, unless you mention it, that the checks, the calibration checks, did not pass. So that's your responsibility. And what does that calibration check involve? We call it the baseline readings. Basically, when we start the CPT, we have the cone hanging in the pusher before it gets into the ground. We basically check that the readings at that time, the zero readings, because there's no pressure on the tip, no pressure on the sleeve, no pressure on the pore water filter. So it's all the zero readings, and the calibration values don't differ more than 5% of the full scale output. So at that time, before you get started, you know that your cone is very close to the calibrated values and that you're ready to go. Then when the cone comes back out of the ground, you check that the reading then, if you still have it hanging free again, doesn't differ more than 2% of the full scale output from the readings that you had taken at the very beginning, so that the initial and the final baseline values are basically the same, which proves the point that the cone was not damaged during that particular sounding. So that's the nice thing about CPT, is that whenever you do a sounding, you know that you have a calibrated cone, and that you also have a firm check that nothing went wrong during the sounding, and that you did not damage your cone there. But it's your responsibility. Where the standard gets kind of wishy-washy has to do with the calibration intervals. Tests for cones used regularly, periodic calibration should be performed. And you can do that based on footage, every 3,000 meters. If you assume that a cone sounding is about 25 meters, so that's about, 75, 80 feet. And that means every 120 soundings or so. Or you can do it based on a time period. But the problem is, some cones you don't use that often. As I told you before, and I apologize for this interruption, as I told you before, when you are dealing with a module behind your cone, it makes sense that you don't remove that module from the cone, that you keep it on the cone, but that then also means that that cone may not be utilized all that often because you don't use that module all that often. And that's where the standard then says that cones that are used infrequently should be calibrated on a time basis. Whenever the cone hasn't been used for a long time, you might check it anyhow, but again, not necessarily a mandatory requirement. And then finally, what the standard says is if you have a project that requires a high level of quality assurance, it's a very sensitive job, it may make sense that you do this calibration before the project. But what you see here, should, may. In other words, there is no real firm requirement. It's something that you have to figure out for yourself. And there's argument for that, because since we're checking the calibration before and after every sounding, you already have some kind of a clear indication that your cone is still in good shape. But you have to keep one thing in mind as well, and it has nothing to do with this standard. Check what your client specs are. There are places where clients basically say you shall not do a measurement with anything that has not been calibrated in the last 6 months. And that suddenly then overrules what the ASTM standard says. ASTM, when it comes to this calibration requirement, is fairly vague. It leaves it up to the user. It gives some guidance, but doesn't make anything mandatory. But keep in mind what your client specs are saying. Next part then is the conditioning. We already talked about that it's important that your filters are fully saturated. And what the code says, you see it in here, this is verbatim from the code, is that you keep it in pure glycerin or silicon oil for at least 90, a vacuum of 90%. So you go down to minus 13 pound PSI gauge, and then you keep it for some time. You can shorten the time if you put some vibration on the whole thing or cool it down. In reality, I would just leave it for about 24 hours in there and make sure that it's fully saturated. Code says that you have to do it. Code gives you some different options in there how you do it. Then the procedure itself, just one aspect in there is that the hydraulic ram feed shall be set to advance the cone. And there you have again the 20 millimeters per second plus or minus 5. Now it gives you some leeway. You can go a little bit faster, you can be a little bit slower, but that is where the 20 millimeters per second that I've mentioned many times is coming from. Now, in reality, time is money. And therefore, most of the time, a manufacturer or an operator will actually push the envelope a little bit, and instead of setting it at 20 millimeters per second, set it at 24, just slightly less than an inch per second. That's perfectly okay, as long as we stick with it. Because you cannot go faster than the 25 millimeters per second. That's outside the standard. It also is interesting, the code is trying to be helpful to you because it says that sometimes if you are in a dangerous or precarious situation, that you see a sudden increase in the tip resistance or a sudden change in the inclination, then it's just fine if you go slower, provided that you clearly indicate it in the report. It does never say that you can go faster. And that's why the warning is don't speed. Because your records show not only the readings for the tip and the sleeve and the pore pressure, it also has a timestamp in there for every time a reading has been taken. And therefore, you can actually figure out when something, how fast you went into the ground. And every now and then there's a reason that a client or some engineer will look at those results and it can actually see that you did stay or did not stay within the standard, and then you have a major problem because then the sounding may not be accepted. So don't speed, stick to that speed. The other reason why it's important you stick to that speed is that we're using these for correlation purposes, and therefore it's important that we operate the CPT under standardized conditions. That brings me to reporting. Code said that if you go slower, and fine as long as you put something in there. And that's why I often use this picture, and with the text that together you're more likely to get good data. And what I mean together is an interaction between the engineer in the office, the guy procuring the equipment, and the guy or the gal, he or she operating the CPT rig. Be honest. If you're out in the field, write down that if something did not necessarily go right, or if there were problems with something that is going on. Be safe rather than sorry. And what I mean by that is make sure that you don't rely upon your memory. Write things down. Put it in your report. Too many notes is better than too few. Then you can always figure out later on whether certain notes are not there. But if you have to think back, if you've been out doing CPT soundings all week, and they suddenly say, well, the one that you did Monday afternoon at 2 o'clock, what happened there? if you've done 30 or 40 soundings that week, you really don't remember. So make notes, make sure that you have all the information there. Now, these are just a few indications of, well, what the code says, what you have to do to stay within the code, to perform CPT in the code. But I come back to what I said at the early part. In the ASTM standard, the whole standard, the word shall, which means that you have a mandatory requirement, something you have to do, you must do it, is used at least 94 times. So 94 times the code says, you shall do this, or you shall do that. And you better make sure that you've done it that way. Obviously, in this presentation, we did not cover 94 times. We covered some of those, the most important ones, and also in the other webinars, we've covered some of this stuff, but there may be other parts, so don't rely necessarily on this presentation. With that, I've come to the end of this, this presentation. Unfortunately, there are a couple of questions that are kind of fairly deep into the whole thing, outside the scope of what I've covered. So I will address those questions separately. There's one more. How slow can you go? And what are the impacts to the results of going too slow or too fast? The impacts of going too fast or too slow are more serious. All the correlations, because we don't take samples, we come up with an analysis of how the soil behaves based on correlations. All those data points have been collected with a 20 millimeters per second. If you go outside that scope, those correlations are not necessarily valid. Are they wrong? Not necessarily, but you don't know. It's kind of like driving through a yellow traffic light. If you are going through that yellow traffic light, most of the time you will not be in a collision. But you're not following the law. You're not following the standard. And you may be involved in an accident because somebody else may already have gotten the green light before you get to the other side of the intersection. So it's not worth it. How slow can you go? There are certain cases where you are going at half the speed, 10 millimeters per second, if you're very gravelly soils or something like that. But there's no firm fixed value there. But 10 millimeters per second, if you are in very treacherous conditions, is something that is realistic. I will leave it at that. The other questions I will respond to separately in an email. With that, thank you very much, and I look forward to talking to you again next month.